Myself Dinesh, MN, Associate Professor, Department of Electrical Engineering, RVCE, Bangalore. I will take you through the initial conditions and the transient analysis as a part of your electric circuit analysis. The previous teachers have taught you the loop analysis, nodal analysis, super node, super mesh and network theorems. They would have taken you through superposition theorem, reciprocity, Thevenin's theorem, Norton's theorem with dependent sources and other things. But one thing is sure, that they would have dealt with all these theorems and all the different types of problems, and the analysis will be only on steady state analysis. This initial conditions, first and foremost, the question is, why is that we require initial conditions? In what way it is going to help us? And what are the different parts of a response? Response, I mean to say, it can be a voltage, it can be a current through a given network. The network consists of simple elements, resistors, inductors and capacitors, along with the active sources. It can be a voltage source, it can be a current source, right. So, first and foremost, we will just try to know the first objective of knowing this particular chapter is why initial conditions. Why initial conditions? First of all, we need to understand, you would have gone through the differential equations. The solution of the differential equation has two parts. The first one is your complementary function and a particular integral. The solution of differential equation. Complementary function means the transient response, and the particular integral means your steady state response. What do you mean by transient response? The response is going to vary with time, and in a particular integral or a steady state response, the response is not going to change with time. I will just like to put one particular circuit on the board and try to tell you what I mean by a transient and a steady state response. If I just take a simple RL circuit, R and L, resistance, inductor and a voltage source. If the switch is closed, the response will be, it will not suddenly increase to a value V by R, the current gradually increases to a value V by R. So, if I just say that the response has reached steady state, and this is in the transient part. So, your response, say for example, it is a current with respect to time, has got two parts, a transient part where the current keeps changing with time, and the steady state part where the current remains constant. So, it is a combination of these two, Cf plus Pi will be your total response of current in case of a solution of differential equation. So, why initial conditions? The question is, why initial conditions? The first one is, it helps you in evaluating the arbitrary constants in your differential equation. It helps you in evaluating your arbitrary constants. In your first order differential equation, you will have one arbitrary constant. In your second order differential equation, you will have two arbitrary constants. As the order increases, the arbitrary constants keep on increasing. This also helps us in understanding the elements, knowing the knowledge of the behavior of the elements, electrical elements, behavior of the elements. Third one, it helps us in understanding the response. we can anticipate the response without actually doing the or taking the resistor, inductor, capacitor and connecting it to a voltage source and then finding out the response using a CRO. I can anticipate the form of response. Response can be anticipated. We will substantiate all this with an example as we go ahead in the class. It also helps us to understand the element's behavior and the element along with the active sources and with other elements. So, we can get the arbitrary constants, we will have a behavior of the elements, we will know the response which can be anticipated. So, the conditions that exist at the time of switching is known as initial conditions. First and foremost, initial conditions means the conditions at which it exists during the switching period. So, if you just take, we have only 3 elements in electrical, that is resistor, inductor and a capacitor. If I just take the resistor as an element, a property of a resistor is it does not allow a flow of current depending on the value of the resistance, right. If the resistance is very high, the current will be low. If the resistance is very low, the current will be higher. So, depending on the value of the resistance, it opposes the flow of current, right. In case of an inductor, first and foremost we need to understand these 3 elements what we have in electrical engineering in a better way. If I ask, many times I have asked my students, what is an inductor? The answer is, they keep telling different answers. It stores energy in electromagnetic field, electrostatic field or whatever, but they will never come, they have not understood an inductor as such. This particular chapter helps you, the initial conditions and transient analysis is going to help you in analyzing the circuit, the behavior of the elements. So, your fundamentals should be proper. An inductor, what is an inductor? Just write down in a book if you have what you know. After some time you will know what the inductor is all about. Property of an inductor is it does not allow a sudden change in current. It does not allow a sudden change. In current. Please note, please underline this word sudden change. This does not mean he is not going to allow the flow of current through it. Many students have this notion that it does not allow AC, DC, nothing like that. These elements are used in both AC circuits and DC circuits. It does not allow only a sudden change, indicates a gradual change is accepted. It allows a gradual change. As I showed you, you can make out in the form of a response. If I just take the response of current as a gradual change, a sudden change is not accepted, whereas in case of a resistor, there is an instantaneous change in current. If I just take a resistor into consideration, there will be a instantaneous change. If I just take a switch, a resistor and a voltage source, if I close the switch, the response will be, current will be 0 before and there will be a sudden change, it will be equal to V by R. If this is R and this is V, there is an instantaneous change. You can just see the difference between an instantaneous change and a gradual change. This is the behavior of your inductor. It will not allow a sudden change as in case of a resistor. So, there is a gradual change, it allows the flow of current. As all of us know, XL is 2 pi FL. In case of DC, your XL will be 0, means there will be a constant current after some time, that we call it as a steady state. It has reached a steady state, means the XL will be 0, but in the transient part it will be opposing the change in current. This is the behavior. If you have still not understood the behavior of an inductor, I would like to give you some more examples. A moving train, you cannot stop a moving train if it is cruising at a speed of 100 kilometers or even 80 kilometers or 120 kilometers. You cannot stop a moving train instantaneously. Once a brake is applied, it gradually comes to an halt. For example, or another example, if you just take Usain Bolt who runs 100 kilometers, even after he completes, he just keeps running for another 50-60 kilometers because he just immediately can't stop the moment of what he has gained. So, the inductor behavior is very much similar to a moving train. An analogous equivalent of an inductor in mechanical is nothing but a mass. So, a moving train can't be stopped instantaneously. Similarly, if you start running, you can't stop instantaneously. If you just apply sudden brakes, all the bogies will be off the track. There will be a disaster. Or another example, a road roller once picks up its speed, it is difficult to bring it to a halt. So, this is how you can understand an inductor in a better way. In spite of that, if you have not understood, I will give another example. Normally, I keep telling my students, it does not allow a sudden change in current. This is very much similar, the behavior of the inductor is very much similar to the way your parents are going to behave. Just go home and ask to buy you a car. The very first instant your father is going to tell you, no, I am not going to get you if you do not have one. Gradually you keep asking, probably with time they might accept your request. So, what is the first instant, the first information what your father gives? If you expect, he just behaves like an inductor. The very first, that means he does not allow any sudden change in current. So, my overall idea is to tell you how the circuit is going to behave in the transient part and in the steady state part. We have three different states here. If you want to say, if I have a switch, I will say that switch is closed at t equal to 0. When I say the switch is closed at t equal to 0, what is the state at t equal to 0 minus? It is before the switch is closed is t equal to 0 minus. The switch is closed at t equal to 0, and immediately after closing the switch I term it as t equal to 0 plus. T is equal to 0 plus is a condition immediately after the switch is closed. 0 minus becomes the history. It can be a switch operation, it can be a closing switch, it can be an opening switch. T equal to 0, the action takes, the switch is closed or the switch is opened. Before that is called as an history. After closing the switch, t equal to 0 plus is said to be the network state at immediately after closing the switch. So, try to understand 0 minus is the history before the switch operation takes place, whether it is closing switch or an opening switch. We will take both the examples of opening or a closing switch as we go ahead with some more examples. Today's class I need to make you understand how the circuit or the element behaves individually, and later on we will take up some examples where we tackle all these things. Now, I told you inductor behaves like your parents. Any sudden change in the behavior of a student is not accepted, but a gradual change is accepted. Similarly, it does not allow a sudden change in current. If this happens to be a current with respect to time and this is your time, always I am interested to know how the current varies with time when the switch is closed. So, this gives an idea how the inductor opposes a sudden change, but a gradual change is allowed. So, how does my element behave at t equal to 0 plus? The equivalent circuit, if I want to substantiate a student that this does not allow any flow of current, means if you just observe what was the current before the switch was closed? Current was 0. The current through the inductor, say for example, instead of R, if I have an RL circuit and the switch is closed at t equal to 0, if it is an RL circuit, the response will be like this. The current at t equal to 0 minus is 0. The current immediately after the switch is closed is also 0. I at 0 plus is also 0. Kindly understand this. There is no sudden change in current. It takes a finite time for the change. If I want to see the current immediately after the switch is closed, immediately after the switch is closed, if I want to write a circuit, the circuit looks like this. The switch is closed, I have an R, right, and if I say the current does not flow, I need to show this inductor as an open circuit only. So, this is what I want to say, an equivalent circuit at t equal to 0 plus. So, the behavior of the inductor will be like an open circuit if there is no current flow earlier. So, I can say that inductor acts as an open circuit. This is what you need to understand. This particular table what I am going to put will help you in understanding the circuits over the next 6 classes. So, this acts as an open circuit. Just because it does not allow any sudden change, the current immediately after closing the switch is also 0. So, effectively I need to represent an inductor in case of an inductor as an open circuit to substantiate that it does not allow any sudden change in current. Therefore, the current remains at 0 immediately after closing the switch. With this, what happens after some time? This is an inductor, it acts as a short. He starts allowing the flow of current. So, the behavior of the same inductor at t equal to infinity, if I say at t equal to infinity, after some time it allows a flow of current, and this current is limited by only the resistance R, and this acts as a short circuit. So, the behavior of the inductor will be like a short circuit when used on a DC supply. So, how do I represent that? I express this at t equal to infinity as a short circuit. But whereas in case of a resistor at t equal to 0 plus, the equivalent circuit, there is absolutely no change, its behavior does not change with time. The behavior of the element, we have just taken resistor into consideration, it opposes the flow of current depending on its value R, there is an instantaneous change in current, it behaves like R even at t equal to 0 plus or t equal to infinity. This is said to be the steady state representation of these elements in initial conditions or in transient analysis. Similarly, if I just take a capacitor into consideration, I have a capacitor. What is the difference between an inductor and a capacitor? First of all, we need to understand 3 elements what we have. All the 3 elements are assumed to be linear in circuit analysis over a given range, means that when I say it's assumed to be linear, means it's just an assumption, it need not be linear. Beyond its range, the behavior is non-linear. But in engineering, we try to solve most of the circuits assuming that they are all linear elements. Linear elements means it should satisfy equation y equal to mx. If it satisfies this equation y is equal to mx, then it is said to be a linear element. Similarly, when I say R is linear, the corresponding equation is v is equal to r into I, is an equation similar to y is equal to mx. If I say inductor is linear, the fundamental equation is phi is L into I, rate of change of flux is your voltage, therefore it is L di by dt, and similarly for a capacitor it is Q is C into V. All these 3 equations are similar to a linear equation, that is why we assume them to be linear over a given range. So, we have understood the behavior of an inductor, it does not allow any sudden change in current. I told you the behavior is similar to your parents. Just go and try, ask something in your house, say that you want a car or something like that. The very first reaction is no, that means your status does not change instantaneously. So, similarly a capacitor, I have a capacitor, the last element what I have, we have only 3 elements in electrical. If you understand these 3, the chapter becomes very simple. So, in case of a capacitor, very much similar to an inductor. If I say he is like a father, he is like a mother. He does not allow any sudden change in voltage. So, he does not allow change in sudden change, I mean to say a sudden change in current. Sudden change is opposed by an inductor. Similarly, a sudden change in current, a sudden change in voltage is opposed by a capacitor. Assume that initially if there is no voltage across the capacitor, even after switching, a similar circuit if I just consider, I have a switch, I have a resistance, I have a capacitor, I apply a DC voltage source. If I close, before the switch is closed, the voltage across the capacitor is 0. After closing the switch, the voltage across the capacitor still remains 0. Therefore, I have to represent a capacitor as a short circuit, not as an open circuit, because capacitor voltage will be 0 immediately after closing the switch. If I want to write an equivalent circuit after closing the switch, I need to write our capacitor as a short, because it does not allow any sudden change in voltage. Voltage at Z minus, voltage across capacitor at 0 minus is 0, Vc at 0 plus is also 0. Therefore, I need to represent an equivalent circuit at t equal to 0 plus as a short circuit, and at t equal to infinity it would have gained charges across these plates, and then finally it will not allow the flow of current, and the final state will be the capacitor would have charged with polarities plus and minus, and the current will be 0. In steady state he acts as open circuit. The current flow will become 0 in steady state. Therefore, in steady state his behavior is an open circuit. If you understand any one, the other one is exactly the same. In steady state he behaves like a short, in transient part at t equal to 0 plus he behaves like a short circuit. At t equal to 0 plus he behaves like open circuit, capacitor behaves like a open circuit. So, these three things should be in your mind, or there is no change at t equal to 0 plus at t equal to infinity. In case of an inductor, because he does not allow any sudden change in current, if it is relaxed, no current flowing through the inductor before the switch is closed, he will not allow any current to flow even after the switch is closed instantaneously, immediately after closing the switch, and at t equal to infinity he acts as a short circuit. Similarly, capacitor. We have two more conditions. I can have an inductor with a current flowing through the inductor before the switch is closed. Two different conditions. I can have an inductor in the circuit without any current flow, so it acts as an open circuit, finally acts as a short. If there is a current flowing through the inductor before the switch is closed, say for example, I will just put one more circuit so that it will help you in understanding. Switch is close to B, it is initially close to A, it is initially close to position A, it has already gone through one transient on steady state. Now, your inductor is acting as a short circuit and the current is limited only to V by R. Now, if the switch is moved to B, after the switch is moved to B, how does your inductor behave? That means, this is a case of an inductor with initial current. Already there was a current flowing through the inductor which is equal to V by R. This is what I mean to say, if there is a current through the inductor, in this loop the current gradually dies down to 0. If we just plot the current with respect to time, the current will be equal to V by R, it gradually dies down to 0. This is how your inductor behaves. So, if there is an initial current, again the same thing, it does not allow any sudden change. Already at t equal to 0 minus there was a current flow through the inductor, it does not allow a sudden change. Immediately after the switch is close to B, the same current will be flowing. Therefore, I need to represent this as a current source of value I naught. I should represent an inductor with initial current as a value I naught at t equal to 0 plus for analysis, and then the final state will be a short circuit. Initially this indicates, this particular symbol indicates that he initially behaves like a current source of value I naught and finally acts as a short circuit. Final states are same, whether it is open circuit or short. This is your short circuit, this is current I naught at t equal to 0 plus during switching. Similarly, when it comes to a capacitor with initial charge, a capacitor with an initial charge across this with charge q because I know Q is C into V or V is Q by C. If there is some charge across the capacitor before switch is being closed, there will be some voltage across the capacitor. It does not allow any sudden change in voltage. Because it does not allow any sudden change in voltage, immediately after the switch is closed at t equal to 0 plus, it acts like a voltage source of value V C. At t equal to infinity, the behavior of the capacitor with initial charge will be V C and finally an open circuit only. It indicates that it initially behaved like a current source, a voltage source, and finally it is behaving like an open circuit. So, this should be there in your mind. These three elements and the behavior should be in your mind. R, there is no change. I reiterate again and again. If you understand this table, the next few problems what we do in initial conditions becomes very simple. Inductor does not allow any sudden change. If there is no current, there will be no current even after switching, immediately after switching. I do not say that it does not allow, gradually allows, it acts as a short circuit. Inductor with initial current act as a current source at t equal to 0 plus, and at infinity acts as a short circuit. Capacitor without any charge will act as a short circuit, because there is no voltage before, there will be no voltage afterwards, and then finally it acts as open circuit after the charge is attained. In case of a capacitor with initial charge, it acts as a voltage source only at the instant of switching, and then acts as an open circuit. This should be in one corner of your mind whenever I take up other problems. Anyway, when I take up other problems, I will write this on one corner of the board, so that you keep referring to this. Now, the question is, we have seen why initial conditions have to be known to understand the behavior of the elements, and in combined networks how the response is going to be. I said arbitrary constants I will explain when it comes to transient analysis. Behavior of the elements we have just now observed. As in combined networks, how they behave in case of RLC, a combination of RLC in series or parallel, or when we analyze the network using a node or a node analysis or loop analysis, we will see how the current is going to vary with time. The response will be a combination of transient response and a steady state response. So, with this introduction, we will just see what is that normally they ask in transient analysis. Normally, they expect you to find the current at 0 plus, the derivative of the current at 0 plus, or the second derivative of current at 0 plus. At 0 plus means the current immediately after switching, di by dt, the derivative of that current, or the second derivative of the current. You need to evaluate all this. We have a procedure. If you just follow the procedure, you get all these things perfectly and with this table in your mind. So, now the question is, why is that we need to know the current at 0 plus, derivative, and the second derivative? What is the geometrical interpretation of these values? It need not be I at 0 plus, di by dt at 0 plus, d squared I by dt squared at 0 plus. It can be voltage at 0 plus, dv by dt at 0 plus, d squared v by dt squared at 0 plus. It can be the voltage across an element, it can be an voltage across a switch, it can be current through any loop, it can be I1, I2, whatever. But what is the importance of I at 0 plus di by dt, d squared I by dt squared? I told you how the response is going to change with time. I do not require a lab to understand the response. Theoretically, I can plot an expected response in case of a given circuit by evaluating the current at 0 plus, the rate of change of current, and the second derivative. I will just take you through the geometrical interpretation of these initial conditions and the derivatives, and let us try to understand in what way these values are going to help us. Apart from getting marks, we need to understand the behavior of the circuit, right. I will just tell you the procedure how to go through for evaluating I, di by dt and d squared I by dt squared. But before that we need to understand why should we find all these things. First, I at 0 plus, V at 0 plus, or it can be a derivative of voltages or currents. If I just look at the geometrical interpretation now, geometrical interpretation of derivatives, say for example I at 0 plus. If I just say, I will give one example. If I at 0 plus is k, where k is positive, it is a positive value, the derivative of this current di by dt at 0 plus is 0, and second derivative d squared I by dt squared at 0 plus is also 0. What does this indicate? I need to know the behavior of the element. I am just using theoretical calculation. I will be finding the current at 0 plus, the derivative and the second derivative at 0 plus. This just tells us we need to have some idea about what is di by dt. Always I will be interested to know the response of current with respect to time. When I say I at 0 plus, this tells me from where the current is going to start. I at 0 plus tells you from where your response of the current in the network is going to start, the starting point. What is your first derivative? di by dt. When I say di by dt, your y axis is I, x axis is t, this gives you the slope, isn't it? When I say di by dt, what is the slope of this particular current? I am telling that this slope is 0. And what is di by d squared I? D squared I is d by dt of di by dt, means the second derivative is nothing but this is slope. When I say di by dt is slope, how this slope changes, the rate of change of slope. So, second derivative normally gives us an information regarding how the slope is going to change. I have a slope. In this case, in this example, we just see current at 0 plus is a constant, some value positive. It can be positive or negative. di by dt is 0, d squared I by dt squared is 0, indicates that the response starts at positive value and there is no change in slope, or the slope is 0 and the change in slope is also 0. So, this represents a similar to a unit step input, a step input. So, it starts at a positive value which is k, which is positive, the slope is 0 and the slope does not change. For those students who have not understood what is slope, I will just in 2 minutes I am going to tell you how to understand which is a positive slope. If we just take 4 quadrants, I will just comment on the first quadrant. If I have a line like this, if I have a line, this is said to be a positive slope, because as x increases, y increases, the slope is said to be positive. For x1, response is y1. For x2, as x increases, y also increases. So, the slope is said to be positive if I have a line or curve like this. So, similarly, what about a line in the other quadrant like this? In this quadrant or in this quadrant, any quadrant, as x increases, this is positive, this is positive, this is positive, all are positive slopes. As x is increasing, y is increasing. So, this is a positive slope irrespective of the quadrant. If the line looks like this, it is positive slope. What do you mean by negative slope? A negative slope is a one where as x increases, y is decreasing. If we just take on the same, just to give you an idea about what is positive negative, this is a negative slope. When x1 is y1, as x increases, y is reducing. So, this is your negative slope. So, what do you mean by a zero slope? So, all lines similar to this are negative, right? It is negative, negative, negative slope. What if it is 0? Zero slope means, first of all, slope is dy by dx, slope is dy by dx. If slope is said to be 0, the change in y should be 0. This is said to be 0 slope, because change in y is 0. There is a large change in x. Similarly, if I say this is said to be an infinite slope, slope is infinity, because your dx is 0. So, this is said to be an infinite slope. So, it is very easy to understand: positive, negative, 0, infinity, right. This is your 0 slope, this is an infinite slope. So, with this I will just give you one more example to understand geometrical interpretation of these derivatives. They will ask you to find I di by dt squared I by dt squared. Another example is I at 0 plus is 0, di by dt at 0 plus is positive, and the second derivative d squared I by dt squared at 0 plus is a 0. With time, if I want to plot this, this gives us an information about the behavior of the circuit elements. It says it starts at 0, this gives you a positive slope, the slope is positive, and the rate of change of slope is 0, the slope does not change. So, it is a ramp. These three indicates that it is a ramp. Another example I will give you. If I at 0 plus is 0, di by dt at 0 plus is k, where k is positive, and d squared I by dt squared at 0 plus is a negative value, the response will be, we can anticipate, this is what I am trying to tell you. If I understand the current at 0 plus, derivative, second derivative at 0 plus as some constants or positive or negative value, I can anticipate the response. It starts at 0, the response starts at 0, it has a positive slope, right. At t equal to t equal 1, the rate of change of slope is negative, indicates gradually the slope is changing. The response will be somewhat like this. This indicates it has a positive slope, for example 10, then it is becoming 8, 6, 5, 4. So, the gradual rate of change of slope is negative, indicates the slope is gradually reducing to 0. So, this will be an expression for current in case of an RL circuit, in a series RL circuit when a switch is closed to a DC supply. So, similarly, if I just say, I will stop this with another example. I at 0 plus is k, which is positive, di by dt at 0 plus is negative, and the second derivative d squared I by dt squared at 0 plus will be positive. Mostly we have taken almost all the cases here. If I just see, if I plot the waveform for current, it starts at a positive value, the initial slope is negative and gradually the rate of change of slope d by dt of di by dt is positive, indicates initially it is negative and gradually it is coming towards 0, indicates a curve like this. It can be, it has a starting point k positive, negative slope, gradually the slope keeps on changing to become, it can be like this or it can be another curve like this. It can, so we can anticipate the response just by knowing the initial current, derivative of the current, the second derivative of the current, or the voltage, derivative of the voltage, second derivative of the voltage. This is what is asked normally given a circuit. A circuit can have a single loop, two loops network. They can ask you to find I at 0 plus di by dt, d squared I by dt squared. This is geometrical interpretation, right. It helps us in knowing the response. I am just plotting all this just by looking at the value of the current. I do not have a CRO. If you want to see the response, I need to go to the lab, rig up the circuit and then capture the waveform and then understand that its behavior. Without doing anything, just by evaluating its derivatives, second derivatives, we can easily understand the response. So, now the question is, with all this theory part, I need to move around and tell you how do we evaluate all these parameters. It can be current or voltage. We have a simple step to be followed, procedure to be followed for evaluating the initial conditions. Probably in the next class we will take up problems and we will go through as per these steps being followed. Steps to be followed, right? Procedure to be followed for evaluating. First and foremost, you need to look at the history of the network. History plays a vital role. History means the network at t equal to 0 minus. The network at t equal to 0 minus means the current and the voltage before the switches operated. It can be plus, it can be a closing switch, it can be opening switch. So, history, find out the current and the voltage at 0 minus, V at 0 minus and current at 0 minus. Keep this in one place. Next, the switch is moved, it can be closing switch, assume that the switch is closed. Write the network at t equal to 0 plus. We know the behavior of the element, how the element behaves as switch is closed. Switch is closed at t equal to 0 plus, write the network at t equal to 0 plus. With these steps we will see how to solve, try to understand what is the procedure to be followed. Later on we will evaluate with the network. In the next class I will repeat these things and we will take up a network, different types of networks what we have, and we will try to solve and find the current and the derivatives which will help us in anticipating the response. So, first thing is we need to know the history. History, if you forget about the history, your future evaluation or the analysis will be wrong. So, before the switch is closed or moved, we need to know what is the current, what is the voltage, because on this the element behavior is going to change or the equivalent circuit of the element is going to change. So, write the network at t equal to 0 plus. As we saw, R behaves like an R at t equal to 0 plus. Inductor acts as an open circuit and finally a short circuit. A capacitor acts as a short circuit and an open circuit. So, with this in mind, if there is a current, it acts as a current source I naught, or as a short circuit with, if there is an inductor with initial current I naught. Similarly, capacitor with initial voltage, it acts as a voltage source with V, and finally it acts as an open circuit. So, with this in mind, what we saw previously, find the network at t equal to 0 plus, evaluate current at 0 plus, voltage at 0 plus. Normally, if there is an inductor, we find the inductor current, if there is a capacitor, we find the capacitor voltage. Normally, this is normal. So, what should we do next? Third step, after finding, evaluate I at 0 plus, V at 0 plus. So, one thing is known already, the current at 0 plus is known to us. Write the general network after switching. General network after switching. means do not represent them by their equivalent circuit, represent them by their normal representation R, L and C. Write integral differential equations. Differential equations means voltage across the resistor is R into I, voltage across an inductor is L di by dt, voltage across the capacitor is 1 by C integral I dt. With this, write either KCL or KVL equations. If it is KCL, you know it is 1 by L integral dV by dt, or C dV by dt. We will see this in the next class, but write integral differential equations. Once integral differential equations are written, fifth, obtain an expression for the first derivative di by dt or dV by dt if they want you to find out the derivative of the voltage. Obtain an expression for di by dt by mathematical manipulation. Rearrange your terms so that the coefficient of di by dt is 1 and obtain a derivative of the current. Using the initial conditions, what we evaluated, evaluate di by dt at 0 plus. So, we know the second one. Sixth, obtain an expression for the second derivative. Second derivative means d squared I by dt squared, means differentiate the equation what you obtained, the integral differential equations, obtain a second derivative, simplify that, and using the initial value of current I at 0 plus, di by dt at 0 plus, obtain the second derivative and so on. This is how we can obtain I di by dt d squared I by dt squared. So, these are the steps to be followed. First thing is the history. You need to know the current at 0 minus, voltage at 0 minus. If there is an inductor, current through an inductor, capacitor, voltage through the across the capacitor. Network at t equal to 0 plus. Using this table, replace the elements with the open circuit or a short circuit. Find I at 0 plus, Vc at 0 plus. Write the general network after switching. Write integral differential equations. Obtain an expression for di by dt. Using the initial conditions, evaluate di by dt. Then obtain an expression for the second derivative either by differentiating this, and then find d squared I by dt squared. Thereby, we can evaluate I di by dt and d squared I by dt squared. So, with this, we will close this session. If you have any doubts, you can contact me. I will give the mail ID and my telephone number in the next class. If you have any doubts, you can just write to me or you can clarify. In the next session, we will take up problems and we will solve. So, come prepared with your calculators, your pen, pencil, paper. Do not just sit and listen, we will solve together, right, and we will see in what way the initial conditions will help us in evaluating. The very first point what I started today was it helps us in finding the arbitrary constant. We will see that afterwards when we get into transient analysis. Right now we are in initial conditions. These initial conditions will help us in evaluating your arbitrary constants of your differential equation, right. So, as the class progresses, things will be very clear. You should be really strong in this particular chapter so that you can understand any circuit. It can be electronic circuits, it can be with BJT, MOSFETs, anything. Analysis of the circuit basically depends on the initial conditions and its derivatives. Thank you.